This is a summary of the second part of class, May 12th, 2020. Earlier, we have learned about the pH grid. That was in part 1 of class. Today, this video is going to teach you about the pH of acid solutions and how to determine strong versus weak acids. I'm going to go kind of fast on this because otherwise the video is going to get really long. So, this is the pH grid. Yesterday, we looked at a demonstration that had a light bulb in it. Remember that light bulb there compared to the light bulb there. So this was what the light bulb looked like when it had hydrochloric acid in it. So that's really bright in hydrochloric acid, as opposed to what it looked like when I pulled the video out the first time with just that's acetic acid. So that's very, very dim. So these are the two acids, HCl. That one was bright. And acetic acid, HC2H3O2. That one was dim. So which one has more ions? This one, more ions. So the reason for that is when you have HCl and you put it in solution, it totally comes apart. So if I have 100 of those, they all go away and I get 100 of these and 100 of those. Acetic acid, on the other hand, hits equilibrium. So there aren't as many ions because the things that are on the right side begin reacting to form the things that are on the left side, and it goes back and forth like we studied last week. So if I had 100 of these, might just get like 98 of those left over, 98, and then 2 of those. And I just made those numbers up, but the point is not all of these react. Most of them stay intact and they come apart, and then these react and go back over here and they react over there. So but you reach a point where the concentration of these is stable. They don't change, there's just not very many of them. All right, so weak acids hit equilibrium, and that's what differentiates strong versus weak. Now, how do we find pHs of acid solutions? So let's suppose I have a 0.02 molar solution of HCl and a 0.02 molar solution of acetic acid. All right, if it's HCl, the reaction is just comes apart like this, H plus Cl minus. So if that's 0.02, it all goes away. That becomes 0.02, and that becomes 0.02. Remember, they all come apart. So if you want to know the pH, you take the negative logarithm of 0.02. Remember the pH grid right here? So if you know the H plus, to find the pH, just take the negative log. So you'd say log of 0.02. So log 0.02 equals 1.7. So the pH would equal 1.7. Now, if you have acetic acid and it's 0.02, it comes apart like this. It hits equilibrium. So that's going to be H plus C2H3O2. And we don't know what the H plus is. We know initially this is 0.02. Before we could say there was none of them to start with. We know that that's going to change by some amount. So it's going to go down by X amount. We just don't know how much, so we just call it X, just like we did last week. And we have to add then X on in both of these cases, because if X amount of this reacts, there will be X amount of that produced. We don't know what X is, but we know that whatever reacts will get the same number of moles produced because of the 1-to-1 ratio. At equilibrium, then, we'd have 0.02 minus X, X, and X. So we need to solve for X. Well, we know the equilibrium constant would equal the H plus concentration multiplied by the C2H3O2 concentration divided by the HC2H3O2 concentration. So the H plus we know is X. We don't know what X is, so we're going to solve it. Acetate is X. And the acetic acid is 0.02 minus X. That's the unreacted acid. And that equals the constant, so we have to go back over to this chart that I linked on the website. Find acetic acid. Somewhere in here. Here it is, acetic acid. And they have the chemical formulas of acetic acid as CH3 COOH, just a little aside. Here's how they think of the acetic acid. CH3COOH. Inorganic chemists usually write, they know this is the H that comes off, so they usually write H, and then that is the last H instead of the first H. So the two O's are there. This C is that, and then CH3 is that. So that's where the CH3COOH comes from. So CH3, boom, COOH. All right, so the constant is what did we say it was? 1.76 times 10 to the negative fifth. See it right here? That's acetic acid. So 1.76 times 10 to the negative fifth equals. Now, in this unit, you're going to be able to ignore the minus x. The reason, it's almost always true. We're just going to assume that it will be always true. The reason for that is if I had like 0.02 minus 0.000045, wouldn't that just be basically the same as 0.02? What happens is such a small amount reacts. You saw how dim the light bulb was. Such a small amount reacts that relative to the original concentration, it's negligible, so we can ignore it. And the advantage to doing that is that it eliminates the quadratic equation, so you don't have to do it. All right, so now we're going to go ahead and solve this. So I'll multiply both sides by 0.02. So I'm going to take 1.76 times 10 to the negative fifth. 1.76 second EE negative fifth. Multiplied by 0.02. And I get 3.52 times 10 to the negative seventh equals x squared. So then you take the square root of that. The easy way to take the square root is to raise your answer to the 1/2 power. So x is equal to 5.93 times 10 to the negative fourth. And if I take the logarithm of that number, since this x now is that, which is that, so if I take the logarithm of that number, remember right here, that's going to give me the pH. So I have logarithm of my previous answer. So my pH would be 3.23. So that's the 3.23 is the pH, which is a negative log of that number. That answer was what we got when we solved for x. X was the hydronium ion concentration, or the hydrogen ion concentration. All right, so that's how you find pH. We're going to do I made a link for you to try a couple of these. So I'm going to reload this page. So a minute ago I had some trouble with it. So we're going to hit new problem. All right, we have 0.91 molar nitrous acid. So on a new page, we'll work through, hopefully this works out with one problem. So we got HNO2. This is a weak acid. All the acids on this link are weak, and I'm going to tell you in a minute how to know the strong versus the weak. But if it's weak, you're going to have equilibrium, like that. Okay, the original concentration, it tells us, is 0.91. And we don't have any of that or any of that. Some of it's going to react. So we're going to get X amount of that and X amount of that. We don't know how much, but it's going to depend on how much of what we started with reacts. Remember, that's initial, that's change. Then at equilibrium, we're going to have 0.91 minus X, X, and X. Setting up the constant, Ka, the ionization constant for acids, H plus, multiplied by the NO2, the nitrite ion, divided by the HNO2 that is not reacted. So we know this is X, this is X, this is 0.91 minus X, and that all equals the constant, which we have to look up. So you go back to your constants, you find nitrous acid, here it is, HNO2, right there. The constant is 4 times 10 to the negative fourth. All right, so we have 4 times 10 to the negative fourth, 4. Oops, the wrong button there. So 4 second EE negative fourth. There you are. Times 0.91, because I need to get the 0.91 out of the denominator. Again, we are going to be able to ignore that minus x because it's going to be so small relative to the 0.91 that it's not important. So multiply by 0.91, 0.91. Okay, so times 0.91 equals, so 3.64 times 10 to the negative fourth equals x squared. Now take the square root of that answer, and you get 0.019. So x equals 0.0191. All right, we're going to go ahead and take the logarithm of that number because remember that's x. X is the hydronium ion concentration. So this number here is that number. So I take the logarithm of that, and that'll give me the pH. So log of the previous answer, the pH should be 1.72. All right, so we go to our answer key, we put in 1.72, and we hit the check answer, and we find that we got the correct answer. So that's how you do the pH of weak acids. All right, now moving on, I need to show you how to tell the difference between strong and weak acids, and then we'll wrap this video up. So, strong acids. There are two kinds of acids that we talk about. One of them is binary, the other one is ternary. So, strong binary acids, there are only three of them. You just have to memorize them. They're HCl, HBr, and HI. Those are the three strong ones, period. Every other binary acid is weak. Now, ternary acids, ternary means three, it's really technically means three. We usually use that term loosely to talk about acids containing three or more elements. So if the O number minus the H number is greater than or equal to 2, we can usually say they are strong acids. And if they're not, the bottom line is we're going to use that guideline. If they're greater than or equal to 2, we're going to call them strong. So here's some examples. I'm going to throw down a bunch of acid down right here. All right, so here we go, a bunch of acids. We're going to identify them as strong or weak. All right, the first acid I wrote down is HF. That's a binary acid. It's not one of these three, so therefore it's weak. The second one I threw down was the HClO2. 2 minus 1 is 1. Is 1 greater than or equal to 2? Nope, so that one is weak. 4 minus 3 is 1, so that's weak. 3 minus 1 is 2, so where does that fall? Greater than or equal to 2. 3 minus 1 is 2. That's greater than or equal to 2, so that is a strong acid. 3 minus 1, strong. 2 minus 1, that's 1, so that's weak because it has to be greater than or equal to 2. H2S, binary. Not one of these three, so it is weak. HBr, binary. It is one of those three, so it's strong. So that's all you have to know to determine strong versus weak acids. Now, why do we care? The strong ones, single arrow. The weak ones, equilibrium, and you got to look up the constant to find their pH. All right, now while we're here, I didn't deal with this in class, but I'm going to deal with it here. So if you have strong bases, okay, it's group 1 and 2 hydroxides are considered to be strong bases, except for beryllium. So what I mean by group 1 and group 2, I'm talking about on a periodic table, group 1 and group 2. So this is group 1, this is group 2. So if I had potassium hydroxide, it's strong. If I had iron 3 hydroxide or iron 2 hydroxide, it's weak. If I had zinc hydroxide, it's weak. If I have rubidium hydroxide, it's strong. Magnesium hydroxide, strong. So group 1 and group 2 hydroxides are considered to be strong. And for whatever amount that dissolves, they dissolve 100%. Now, some of the second column ones are not very soluble in water, but for whatever does dissolve, they also dissociate. All right, so group 1 and group 2 hydroxides are strong. All other bases are weak. All right, so in this little session then, what I tried to do was teach you how to find pH of acid solutions. We talked about pH of strong acids. Those are easy because all you have to do is look at the concentration of the acid, and that becomes the concentration of the hydronium ion, like this one. So if you knew the concentration of the HCl, that's the concentration of hydronium ion, just take the negative log of it. But if you have a weak acid, then you have to ice it, solve for X, and then take the negative log of your X. So if it's a weak acid, you ice it, solve for X, take the negative log of X, and that gives you the hydronium ion. X is the hydronium ion, then take the negative log of that, and that gives you the pH. And last thing, what's the difference between strong and weak acids? And we just went through that. So that's how you tell the difference. And that's the end of part 2 of class today.